Okay, Daniel, are you ready to present? Are you ready to do the presentation?
Yes, Prof.
Okay.
Can you see my Word file?
Oh, yes, thank you. Very clear.
So the number 3, I make distributed model with 4 legs like this. And B is dynamic model. And my conclusion is like normally in a small sample, because we have like 2 alternatives. And according to the alternative 2, in a small sample like this case, we have like 25 samples, dynamic model is better used. But it is easier to have a serial correlation problem. And
excuse me,
yes.
Daniel.
Yes.
Okay, let me see the A part.
Yes.
How come you just have only 21 observations?
Oh,
It's 25.
Did I get it wrong? Because like at first when I do the Excel, it says that I should start from 1985. So when I look at the file, so I see that there are some numbers missing on the Excel file, so I just cut it.
Oh, really?
Yeah, and I think it's wrong.
Let me see.
Because on the file, like we're starting from 1980.
Let me see
I remember.
See the data.
Okay.
Use mouse. But let me share my screen.
Okay.
What's the data looks like? So Daniel, did you see my screen?
Yes, I see.
Okay. So according to the questions,
It said that we should start from 1985. So I thought that the data is not good enough, so I just cut like from 1981 to 1984, and I start with 1985.
oh, okay, I understand this. Now, since we have 4 legs, therefore you're using original data without cutting 81, 82, 83, and 84, then you can use the legs AD from the original data, right? So do not cut it off.
Okay.
You know, even we don't have cells from 1981 to 1983, but still we don't use the data. We don't need that data for estimation, right? But we do need the data from 81 to 84.
Okay, I got it.
Okay, so just use the original one. You know, one thing better doing the packages is that if you didn't really care about your data, then the computer will have all the observation they wanted. So they will eliminate it. You know, the computer will eliminate it for you. You don't have to do it by yourself.
Okay, I got it.
Okay, all right. So since you eliminate this 4 years data, therefore you just have those 21 degrees of freedom sample sizes. Okay, understand it. Okay, let me get out of here and let me okay, I'll put the screen back to you. Okay, then continue your presentation, please.
Okay. So I think like maybe the rest is wrong, but so number 4, I test the correlation from the dynamic model. So I have hypothesis, and I got the result is the chi-square is 0.0134 is smaller than the critical value is 2.74 because the degree of freedom we have here is 1 and 10% in the table B6. So we
okay.
cannot reject the null hypothesis.
Okay.
And number 5 is building dynamic model. So we have like the first order autocorrelation coefficient is like this. And the second order will be added one more lag variable. So, and in the Lagrange multiplier test for the zero correlation, second order zero correlation, lag would equal to 2. And the B formula for this one is nearly the same as 12.18, but I added like this one, the time lag. And the dynamic model from C is I do it with like 2. And I have the same result at number 4 is we cannot reject the null hypothesis.
Oh, all right. All right. Okay, thank you. Thank you very much.
Thanks, Prof.
All right, so it's Linda. Linda,
Yes.
it's your turn.
Okay. Wait a minute. I should use the screen, right?
Yeah, you need to share your screen.
This one?
I haven't seen the. Yes, okay. All right. Can you enlarge a little bit?
Sure. This is
Bigger? Oh, yeah. Okay. Thank you.
okay. In
All right.
the question 3, we need to have the distribution that model have 4 legs, and this is a result. The result is not really great because we can see that, as other classmates said before, this result need to degree one step by step. So I think this result is not really great result. And
It's not
this
match with
one,
the expectation.
yes, and this one is dynamic model, and this is a result.
All right.
Okay. In the question 4, we need to test for the serial correlation, and this is a result of Tesla serial correlation, and we can see that our n is 24, and our r squared is 0.00039, and we need to plus the 24, which is our r squared, and we can get the result is 0.02, and this is smaller than 3.84, which is percent critical chi-square with 1 degree of freedom. So we cannot reject the null hypothesis of non-serial correlation.
Excuse me, okay?
Yes.
Let me see the there's 4 parts. Okay, question number 4. Yeah, okay. And roll down a little bit. All right. And LM is N times R squared, right?
Yes.
And the N, it should be 25.
But I think the textbook says they need to minus 1, so the N
Really?
will be 24.
Really? We need to minus 1? Let me see.
391.
Let me see. Excuse me.
Because they say the the original size of this model is 32, but this model is used 31. So I think they need to minus 1.
No, excuse me. I have to mention it here, okay? And the one using on our textbook is Stella. I mean, the package is Stella. Okay? Then, I think they're using, when they do this work on this problem, the computers from Stella, they will consider the lag, but for e-views, okay, for e-views, or for Grados, we're just working with, okay, they are using the original sample size. So instead of using 24, you need to use 25, okay? And actually, it's already done from the Grados. How do we know that? Did you see in the middle parts, okay? In the middle parts is TR squared equal to 0.000963. Did you see the numbers, Linda?
Yes.
Okay, this is already using 25 times the R squared. You can see is 0.00000039. Okay, it's already done it. So you don't have to do it by yourself again. You see what I mean?
Yes.
They already did this one in the middle parts. In the middle parts is what we have to see the result, right?
Oh, yes.
They already calculate the numbers. Although you are using the R squared times T, it's not exactly what you have it. It's because the computers, this is 0.00039. There are some decimal places. It didn't show it up, okay? So the computer already calculate the numbers here. You don't have to do it by yourself. And all the p-values, it's already showed it here. It's 0.975. Although you wanted to use the critical value approach, you need to use just the numbers they're calculated, which means 0.000963 compared with 3.84. You see what I'm saying here?
Yes, right. I miss it. Okay. Okay, I know.
Okay. Okay, although you know
And
it's
I
also not
totally
it it also not wrong if you do it by yourself. But here, since we do have some you know, a little bit different procedures from Stella and also from Grados. Therefore, we do have one observation difference here. So
Okay.
in the Grados, you just have to use 25 instead of 24. But you know, from Stella's point of view, they are using 24.
Okay, I know. So this is
Okay,
a
understand what?
different. Yes.
So understand what I'm saying here? It's
Yes.
not. Yeah. Okay. Okay. So this is not really wrong, but you have to be careful about it. Okay.
Okay. And in the question 5, A part, what the meaning of we need to use the second order serial correlation? Because second order serial correlation, which means the type periods will affect data result. Generally, like after serial will be then tertiary after first order or second order. And the B is the equation of this model. And the C, I do the second serial correlation, and this is the result. And the result shows, okay, we just miss it. We can see they have the zero, they have the n minus, they have the 1.4596, and is also smaller than 5.99, which is the percentage critical chi-square with the 2th degree of freedom. So we also cannot reject the null hypothesis of the serial correlation.
Okay. Thank you very much.
Thank you.
All right. It's Catherine's turn.
Okay.
Okay. Enlarge a little bit. Okay. Okay. Good. Good. Thank you.
Okay. In 3A part distribute leg models for 4 legs. We have equation like this one,
Mhm.
and we add 4 legs for AD, and we do the cells for dependent variable. And in here, we find the result is a match the economic theory because there is some vertical correlationality between the leg x.
Okay.
And the B part of dynamic model. And the 4, we run this one. And the 0.00963 will be less than 3.84. So we cannot reject the null hypothesis of no serial correlation.
Okay.
And the part 5, second order serial correlation is where an error affects data 2 time periods later. This can happen when your data has seasonality. Other orders higher than second order do happen, but they are rare. And this one, there are 2 degrees of freedom in such an LMSC test.
Mm-hmm.
And the part C, also the 1.4596 is less than 5.99. So we still cannot reject just as the result of 3B.
Okay, good.
Thank you.
All right. All right, so it's all the presentation finished, okay? And I really encourage all of you to read the chapter 12 from the first page. I mean, the entire chapters from line to line. Okay. I'm not sure that, especially for master students, we are not familiar with the time series data. So I think this is the first time you will get involved with the time series model. Okay. So I really encourage all of you to read it. Chapter 12, the entire chapter from line to line. And so far, we have covered 12.1 up to 12.4 actually. And I would say that starting from section 12.4 is getting more difficulty involved. Okay, it's more complication involved. Therefore, I think I already explained it. Range of causality last week, and I also put excuse me, did I share my screen?
You have improved.
No?
No, okay, sorry, just a second, okay? I share my screen first. Okay, then did you see my screen now?
Yes, bro.
Yes.
Okay, I think I already upload this PDF file about the Granger causality, which I mentioned it last week. Okay, and I'm just finished this Granger causality last week by theory without any example. And the reason for that, okay, the reason for that is to perform Granger causality, there are some some conditions or factors we need to consider before we perform the Granger causality. Okay, which is I also put this 5 points here, and I like to remind it again now. All right. And we say that we implement the Granger's test, we need to consider several factors. Okay. The first one is the number of lagged terms to be introduced in the Granger causality test is an important practical question. This is what we are saying. When we do the Granger causalities, for our examples, we need to do 12.20 and 12.21. In other words, using y as a dependent variable and also using a as the dependent variable to check the null hypothesis, like alpha 1 up to alpha p equal to 0. And against the alternative hypothesis, at least the one alpha j is not equal to 0. Okay? And how many lags means what's the maximum of p here? We have to decide it before we do the Granger causality test. I mean that before we do the Granger causality test, we need to set up the equation like 12.20 and 12.21. And this two is all involved the maximum lag of P here. Okay, all right. And because the maximum because it is important, because the direction of causality may depends critically on the number of lag terms included in the model. And in order to do that, we will have to use like archaic Schwartz or similar criterion to determine the length of the lags, and or some trial and error is inevitable. And we will do these procedures when we do the real examples. Okay, I'll teach you how to looking for this criterion in order to decide the lags of the terms. All right. Second, we have to assume the error terms entering the gradual test are uncorrelated. Means that we need to assume and we have to make sure this error terms is no serial correlation problem involved. If these two error terms do have serial correlation problem involved, then we cannot do the gradual causality test. We need to do something else to fix the error terms. Okay, so this is the second one. We need to be careful. The third one, we have to guard against the spurious causality. In other words, we need to make sure the equation 12.20 or 12.21 are not spurious regression. And in order to do to understand or to know whether this regression is spurious or not, we are going to talk about in section 12.5, which we haven't get to that yet. Okay, so I need to do the section 12.5 in order to make sure the equation 12.20 and 12.21 are not spurious correlation. Okay, so this is number 3 here. And number 4 is related to number 3. And we say that the critical assumption underlying the gradual causality test is the variable under study, such as A and B, are stationary. So again, this is also another term we haven't learned it yet, and we will learn it. We'll cover it in section 12.5. And this stationary is related to spurious. Okay, and this number 5, if we check the individual variables under study are non-stationary, since number 4 conditions say that it should be stationary. But if we find, after we do the test, if we find those variables under study is not stationary, in other words, it's non-stationary, then what do? We need to know this is possible that the variable is in question are co-integrate. So this one, co-integrated, is also covered in section 12.5. So in other words, if we want to implement the gradual causality test, we need to, fix all these 5 points before we do the gradual test. And all of them we will show, especially for spurious, for stationary, and co-integration. Those concepts I'm going to cover in section 12.5. Okay, then after I explain 12.5, then I will give you the whole examples which covers all the spurious test, stationarity test, and also co-integration test. Then after all, we have done that, then we do the gradual causality test. Okay, understand what I'm saying here? All right.
Just
And excuse me, any questions?
No.
Okay, okay. And for this 12.5, section 12.5 is really heavy, okay? Especially for those master students. But, you know, I cannot overemphasize this one for PhD students also, okay? So read it carefully and review it carefully, okay? Then after we finish 12.5, I do the examples. Then I will give you another assignments to work, especially for all this test. Okay? All right. Then now if you don't have any questions, then let me come back to our section 12.5, starting with the spurious correlation and stationarity problems. Okay, let me start this one and let me do this one and let me see this one and let me do the okay. All right, this started section 12.5. Okay, what do we mean by spurious correlation? Okay, a spurious correlation is a strong relationship between two or more variables that is not caused by a real underlying causal relationship. In other words, for if we do a regression, the y variable, we usually we have a set of x variables, and we do have y variables. If we see the significant relationship, means strong relationship between y and one or several x variables, but it is not caused by the real underlying, I mean, in according to the theory, it is not caused by the theory. Then we also see the strong relationship between y and x, and we may suspect there is a spurious correlation. So a regression in which the dependent variable and one or more of the independent variable are spurious correlated is what we call spurious regression. And what happens if we do have the spurious regression? Now we know that the t-score and the overall fit, I mean the r-square, are likely to be overstated and untrustworthy. It means that all the significant t-score or the higher r-square values are just overstated and is not reliable. And we need to understand that one important cause for the spurious correlation or spurious regression is called non-stationarity. Okay? Then let's see. What is non-stationary? We do have non-stationarity, the terms. Okay? Without the non means stationary. So if you look at your textbook on page 395, okay, we do have the definition for stationary, and which also put on our PPT PowerPoint. Okay, so a time series variable xt is stationary if three conditions met. Okay, these three, also we say three properties. The first one is the mean of the xt is constant over time. The mean of the xt is constant over time. Okay? The second one is the variance of the xt is constant over time. The variance of the t is constant over time. The third one, the simple correlation coefficient between xt and xt minus k depends on the length of the lag k, but on no other variables for all k. Understand what's the meaning of these three properties? The simple correlation coefficient, number 3, the simple correlation coefficient between xt and xt minus k depends on the length of the lag t. Okay, for example, xt is the current periods. If we have the k equal to 2 means 2 periods. So the current periods x, the simple correlation coefficient between xt and xt minus 2 depends only on the legs of the length of the leg t, k, because it only depends on these 2 periods instead of other variables. Okay? All right, if these 3 properties met, then we call stationary. And if one or more of these properties is not met, then xt is called non-stationary. And if we do have the variable xt is non-stationary, we know this is a problem of non-stationarity. Okay? All right. So the next question we're thinking is, why should we worry whether a time series is stationary or not? Why do we have to worry whether a time series is stationary or not? There are 2 reasons. Is there anything that in this PowerPoint? Okay. Okay, I'll mention there's 2 reasons to worry about the time series is stationary or not. The first one is, if a time series is non-stationary, then we can study its behavior only for the period covered, only the period under consideration. In other words, if we have the time series for xt, for example, xt is non-stationary, okay, we can study the behavior only for the period under consideration. Means that if this just current and the previous one and the second period, then we can just study the behavior only for this period only. As a result, it is not possible to generalize it to other time periods. If we want to study, which is not just only two periods, we study only 5 periods. I mean, the first one, from the second one to the previous 5. Then it is not possible to generalize it to from 2 periods to 5 periods if we have these 2 periods variables is non-stationary. And in other words, usually for time series data, the forecasting purpose is very, reasonable, and so always expecting to do the forecasting purpose. Therefore, if you can not extend generalized what you have studied to other time periods, then for forecasting purpose, usually is little practical values. Okay, so in other words, if we have the time series data is non-stationary for forecasting purpose, non-stationary time series will be of little practical values. Okay? The second reason to worry whether the time series is stationary or not is if we do have non-stationary time series, we will lead to the phenomenon of spurious regression. Okay, so I already mentioned that if we have the spurious regression, means that they do have higher R square, they do have higher T values or F values. But unfortunately, these tests are not reliable. Okay, all right. So this is the reason that we need to worry whether a time series is stationary or not. Okay, I'll mention again. One is for the forecasting purpose. That doesn't work. Okay, the second one is all the regression result according to the spurious regression. All this result is unreliable. Okay, and we do know that some of the variables are non-stationary because they rapid increase over time. And in that case, you can add a time trend to the regression model, and that will help to avoid spurious regression in this case. Okay, if you happen to have a variable which is, non-stationary because of rapid increment, then one way to solve the problem is just add one time trend variables into the regression model. What do we mean by time trend variables? Means we can put another variable named time, and we put, for example, if I have 30 years data. So in other words, we have t from 1 to 30. So use the time variables denoted as 1 to 30 as a variable and put it as an independent variable in the regression model, and to avoid this spurious regression factors. But this is not always, we can do it. So sometimes, unfortunately, many economic time series variables are non-stationary, even after the removal of the time trend. And in that case, this cannot alleviate the non-stationarity. Okay, and if we understand in economics situations, this non-stationarity often takes the form as a random walk. Okay, non-stationarity often takes the form of random walk. Now, let's explain what is random walk. Okay, and let's see. Okay, this is what we have on our textbook on page 396. First of all, look at equation 12.22. Okay, look at this. Okay, this is the expression of the current variable yt has a relationship with the previous y. I mean the previous last periods. Okay, the relationship with the current t has a relationship with the last periods. Okay, and we know that this gamma is the coefficient between the relationship between yt and yt minus 1. Okay, then what do we see? Look at the gamma. If the absolute value of the gamma less than 1, so what does that mean? Means this gamma is between -1 to the +1. Therefore, since it is less than 1, means that gamma, even positive or negative, which is between, is a decimal place, is the decimal places, means this is smaller than, is from fractions. Okay, so in other words, if I have y less than 1, means the expected value of the yt will eventually approach to 0. And therefore, yt becomes stationary. Okay? If gamma, absolute value of gamma less than 1, means yt is stationary because yt will eventually approach to 0. Similarly, if absolute value of gamma greater than 1, means gamma is greater than 1 or gamma less than -1. So what did you guess? The expected value of the yt will continually increase or decrease. Continuously increase or decrease. Then there's nowhere to go. We don't know where to go for the yt. Therefore, yt is non-stationary. Remember that the definition of the stationary means that the mean is constant over time. The mean of the xt, if there's a variables, you don't know where to go. Okay, then the mean will not be the constant. Okay, then if we don't know the x, what this variables will drift to, then the variance of the variable is not constant. Okay, and these two properties is also violated the definition of stationarity. Okay, therefore, with absolute value, a gamma is greater than 1, then yt is called non-stationary. Okay, and there's one case which is the absolute gamma equal to 1. In other words, either gamma equal to +1 or -1. Okay, means that the current value of the y is the same of the previous one. The previous one, okay? Or the current will be the same as the previous one, but just the opposite sign. And in this case, there's a special name called unit root. Okay, in that case, gamma equal to 1. And we call this one is random walk. Okay? So equation 12.23, if we do have the relationship between yt and yt minus 1, it's like 12.23. This is what we say is the random walk. In other words, the expected value of the yt always equal to the previous one or the opposite direction of the previous one, then YT does not converge on any value anyway. Therefore, Y is also non-stationary. So in other words, only the absolute value of the gamma is less than 1, then YT is called stationary because they will converge eventually to 0. But there's two situations. One is just exploded to anywhere, to any directions. And this one is just the same as the previous one. So there's no the Y will not converge to any values. And we call equation 12.23 is called the random walk. Okay, and the gamma equal to 1 is called the unit roots. So if a variable has a unit root, then the equation 12.23 holds, and the variable follows a random walk, and it is non-stationary. Therefore, the relationship between unit roots and the non-stationarity is so strong that some econometricians use the words interchangeably, even though they recognize that many factors other than unit roots can cause non-stationary. Okay, so unit roots is one of the reasons to cause non-stationarity, but the relationship is so strong. Therefore, we usually say random walk or unit roots interchangeably. Okay, I'll stop here today, and please go back home and review it. And I'm going to using some examples to do it from next week. Then we will do more this stationarity test, or what we call spurious regression test. And also, finally, I'm going to introduce the co-integration. Okay?
Yes,
All right.
ma'am.
Any questions so far?
I want to ask you about the homework assessment. Usually,
Excuse me.
I want to asking.
Yeah.
About the when we use lag 1 and when we use lag 2, bro.
Oh, you mean the lag 1 or lag 2?
Yes.
Well, usually, again, it is also depends on the variables, the behavior of the study, and we know that sometimes most of the time we know the number of lag by the theory. Okay, yeah. And I'll show you some examples which we can use some criteria like Akai and Schwartz, something like that criterion, and look at the result and decide the lag of the periods. Okay, so I'll show you something next week.
Okay, bro. Thank you.
Using the examples.
Yeah.
Okay.
Okay. Thank you, bro.
All right. Any questions?
Professor, we are not able to download the note about the Granger causality. We're not able
really?
to do it. We just Do you think you can put it in the line group so we can download it?
Oh, sure. Let me just put this PDF. I have the PDF which I put on the okay, let me do it right now. Okay, let me do it right now. Okay.
Thank you very much.
Let me do it. Okay, I'll do it after the class because I don't have
Okay.
line here. Okay, okay, I'll do it right away after the class.
Okay, thank you.
Okay. All right. No. Okay, let me get rid of this one. Go back to. Okay, let me stop the recording.